Oh, hi, welcome again. This is our chapter 4 lecture. Today, I want to get started with part A as usual. There are two parts for every chapter. Part A, which will cover section 4.1 through section 4.3, and part B will cover section 4.4 all the way to 4.6. And without wasting my time, I just want to kind of like break down, explain the title of this chapter. In the previous chapters, we looked at how to write chemical formulas for compounds, uh, Palan's chemical equation, and it's going to be the central in order to understand what is going on in chapter 4. We will need to revisit those concepts, and I believe you have mastered them. Now, chapter 4 is reactions in aqueous solution. Well, so far, a general chemical reaction is represented by chemical equation, generic A, and let's say A plus B in aqueous phase to form C maybe solid plus D here gas. So just give you a generic. These represent a chemical reaction, chemical equation represent and you may see numbers, of course, in front of each reagent, just general numbers. These represent the uh, mole ratio in chemical reaction. They are the coefficient in the balanced equation. This represents a chemical reaction. But now, what do we mean by aqueous solution? An aqueous solution, solution is a solution. This is a solution where, all right, H2O, H2O is solvent. That means the dissolving media is H2O. The dissolving media is H2O. Underline the word H2O. If you use other dissolving media other than H2O, and then there is a different solution. But aqueous solution is a solution where what? Where H2O is used as dissolving media. Now, this is the roadmap for chapter 4, general properties of aqueous solution, which I've explained what an aqueous solution is. We look at the precipitation reaction. Some reaction form solids. When you mix A and B and a solid fall out of the solution, we call those precipitation reaction. We'll look at the special type of double replacement reaction, where an hydrogen ion combined with hydroxide ion to form H2O. We call that acid-base neutralization reaction. And then section 4.4 is on oxidation reduction reaction, abbreviated as redox. This is a reaction where there is transfer of electron. We look at how to keep track of electron being transferred. And 4.5 will dive into concentration. Is a unit of expressing the ratio of the solute moles or number of moles of solute in a given quantity of solution. And finally, solution stoichiometry. We will extend the stoichiometric calculation we covered previously to the volume, So what are the general properties of aqueous solution? Remember, aqueous solution are solution. We'll use this AQ, H2O is the solvent dissolving media, all right? We call that aqueous solution, abbreviated AQ. Solution are defined as homogeneous mixture of pure substances, of which at the outset you'll look again in Chem 2. solvent plus solute, all right, equals to solution. So when you see the homogeneous, we defined earlier on heterogeneous, homogeneous mixtures, but solution is an homogeneous mixture of two. Solvent is present in solvent is present in large amount, all right? And this one is present in small amount. You'll cover in details in Chem 2 more about solution, but for now, understand that the substance which is present in large amount is considered as the solvent, whereas the solid or other substances rather are referred to as solid present in small amount. Okay, doesn't mean the most students construe that or think that always the solvent is in liquid form and solute is in solid form. That's not the case. Air, for example, is an homogeneous mixture of different gases, nitrogen being the predominant, and then we have other trace amount of gases, for example, CO2, gaseous H2O. The one present in large amount is the solvent. The one present in small amount is the solute. Okay. You can also have solid-solid solution. For example, alloys. That's a mixture of two metals, right? So if one is present in large amount, that is considered as the solvent. The other one is what? Is the solute. Or we can have liquid homogeneous mixture. The one present in large amount will be the solvent, and the one present in small amount is the solute. For example, ethanol and liquid H2O, both of them are in liquid phase, all right? The other one can be, depend on how it's prepared. The other one can be the solvent, the other one can be the solute. So don't think that always the solvent is the liquid, whereas the solute is the always solid. That's not the case. You have to use the relative amount of which. Now, when water, H2O, is used as the solvent, we call this, or we consider that solution as aqueous. That's the most important point to remember. All chemical reactions we will look at in chapter 4 are in aqueous phase, which means H2O will be used. This is, I can tell this is on the diagram here is an homogeneous solution of what? Methanol, which is an alcohol, and liquid H2O. I can tell by the composition. Recall what I said, the white sphere here, hydrogen, the red sphere here is the water, and then this is the water molecule. Methanol, there is one carbon, so I see the black one here, but nevertheless, what the message here is the composition homogeneous mixture of two or more substances. So depending on which one is present in large amount, we can designate that as solvent and solid. Both of them, they are in liquid phase. So aqueous solution can, can vary in or can be in different forms. Substances can dissolve in water by different ways. We have the molecular compounds, we have the ionic compounds. Go back to the two classes of compound we covered before. Ionic compound here consists of metal, all right, plus non-metal. Metal plus non-metal gives you ionic. This is ionic what? Ionic compound. And this ionic compound dissociate or dissolve by dissociation when water surround the separated ions. It's important to understand the molecular geometry of H2O. Recall this from Intro to Chem, you did a lab on molecular geometry, the hydrogen, and oxygen on this side. Hydrogen. There is a partial what? Partial positive charge, and partial negative charge. Where this arises from is from the fact that oxygen is more electronegative. It pulls electron toward itself. Therefore, each hydrogen is electron poor. That means in this bond right here, I'm trying to show you where the bond here, electrons are pulled toward oxygen. Electrons are pulled toward oxygen. Now, this is electron-rich portion of the water molecule. And let's say an ionic compound such as sodium, all right, and sodium chloride, it will dissociate into sodium ion and chlorine ion. The water molecule will surround, let's see, this is sodium, all right, and the water molecule, since positive and negative from classical physics, positive and negative to attract. Therefore, water molecules will surround. So these are oxygen, oxygen, and I can have what? Hydrogen, hydrogen, here, hydrogen, hydrogen, and here is what? Here is hydrogen, hydrogen. If you look at how the sodium ion is surrounded by water molecule, they get associated with what? Oxygen, which is negative from this structure, it's negative. The surrounding, take this arrangement, the surrounding this arrangement. When ions dissociate from the ionic compound, if we have chlorine, which is what, or chloride rather in water molecule, it will get associated with what? Hydrogen. If you look at hydrogen, I'm just giving you an idea of how this is oxygen, hydrogen, and I can have oxygen here and then hydrogen there. The chlorine is associated or surrounded by water molecule using the hydrogen negative. Remember, this was partially positive. This is chlorine positive and negative to attract. So understand the surrounding of the solid ions by the water molecules. Molecular compounds, these are compounds made up of what? Made up of non, all right, non-metal compounds, such as glucose, such as sucrose, for example. When they dissolve, they just exist as molecule. Some molecular substances react with water when they dissolve. For example, our acids, HCl, will dissociate into hydrogen ion and chloride ion. Therefore, take into account, we will look at it later on that some molecular compounds do what? Some molecular compounds also dissociate to give ions. There is a key term here, and by the way, the bolded terms you need to be able to define. You may see in the exam or in the quiz asking you the definition, and some of them, they are highlighted in my PowerPoint slide. For example, here, solvation, from the word solvation, from the word solvent. That means the process by which the solvent molecules surround the solute particles when they dissociate in the solution. We call that solvation. For example, on the PowerPoint or on the whiteboard here, all right, on the whiteboard, I do have the solvation of chloride ion, the solvation of what? Solvation of sodium ion, surrounding the solute by the solvent. Now, this solvation is general term because it varies from solvent to solvent. If water is the solvent, we call this hydration. You know, hydration, you have heard about being dehydrated. When something get dehydrated, that means water molecules is driven off. So here is a typical example of hydration. The blue spheres represent sodium. And if you look at how the water molecule orient themselves around the sodium cation, they use oxygen to surround it. If you look at the chloride, the green spheres on the PowerPoint slide represent what? If you look at the green, all right, green spheres here, hydrogen get associated with the chloride. This is negative, this is positive. We say that this is the solvation, all right? This is a solvation with solvent, but if it is water molecule, we say hydration. So here, hydration is simply a process by which water, all right, water molecules in solution. So if you are using H2O, we say hydration, but if it's just general solvent, we say solvation. Now, I need you to be able to divide hydration, you know, distinguish between solvent and solute. Still on solute, we have those ionic compounds, which when they dissociate in H2O, they conduct electricity. We call those electrolytes. Stable sodium chloride, when dissolved, it complete electric circuit. Therefore, there will be light. We call those electrolytes. And electrolytes are compounds which dissociate or ionize completely when dissolved in H2O. Dissociate. In other words, the dissociation here, for example, sodium chloride using steel again, this will dissociate into Na, and then you see aqueous like that plus that plus Cl negative aqueous. It means now each ion is surrounded by water molecule. So this is surrounded by water molecule. This is surrounded by water molecule. We have weak electrolytes. We'll see later on examples of strong electrolytes, and mostly they are ionic compounds. Now, weak electrolytes, they partially dissociate. They do not dissociate, so their electrical conductance is weak. If we use a weak electrolyte in this experimental setup, the bulb will be dim. It wouldn't be as bright as when we have a strong electrolyte. Non-electrolytes, they do not conduct electricity. For example, sucrose, it's the sugar, okay? They do not conduct electricity. Likewise, you know, H2O, pure H2O, it is it's non-electrolytes. They do not conduct electricity. Now, compounds such as sodium chloride, we consider those as strong electrolytes. On table 4.3, please look at table 4.3. Summary of electrolytic behavior of common soluble ionic compounds and molecular compounds. Let's see, when we say strong or ionic compounds, that means you have a metal and a non-metal, okay? are all electrolytes. If there is a metal plus a non-metal like that, this will what? This will give ionic compound. All right, ionic compound, and this is strong. We say that this is strong electrolyte, strong electrolytes. Unless you know, if you cannot distinguish between a metal and a non-metal in a compound, therefore, you know, you'll have a challenge classifying a compound as any compound. Therefore, you will be in a dilemma whether to classify that compound as electrolyte or non-electrolyte. Now, molecular compounds, all right, are strong acids. So you need to know what are strong acids. On table 4.2, these are strong acids. We will come back to, or we will look at this when we get to acid-base neutralization. HCl, for example, is a strong electrolyte. Hydrobromic acid, for example, just to give you hydroiodic acid, aqueous, all right, sulfuric acid, all right, you should be able to, by the end of chapter 4, you should be able to classify an acid as a strong acid or a weak acid. And these are just to give you a few examples of strong acid. Now, weak electrolytes include weak acids, all right, weak acids. And you should know by end of chapter 4, if you look on table 4.3, acetic acid, for example, this is acetic acid, CH4. We call this acetic acid. It is a weak acid, weak electrolyte. HF, this is what? Hydrofluoric acid is a weak electrolyte. Nitrous, HNO2, aqueous, and by the way, this is also aqueous. We call this nitrous acid. Just to give you a few examples so that when we say weak acid are weak electrolytes, these are examples of just few acids. And then our bases are weak base here, all right, weak base. This includes ammonia, NH, or ammonium hydroxide. For example, NH3 like that is the same thing. It's the same thing. This is ammonia gas dissolved in H2O. Produce ammonium hydroxide. This just give you, and it's a weak what? It's a weak electrolyte, weak electrolyte. The rest here, all other compounds are non. So you should know what constitutes strong acid. I've given you example. Look at table 4.2. I've given you examples of weak acid, which are weak electrolytes, and a weak base, which is also weak electrolytes. So you should know the difference between strong electrolytes, weak electrolytes, all right, and then non-electrolytes. The reason why strong electrolyte conduct electricity is because the substance dissociate into ions, and positive cation move towards the negative, the anode, and the positive move to the cathode, which is the positive on the terminal. We're gonna look at that in chem to conduct electricity. Non-electrolytes, they do not, even though sometimes they dissociate, they do not produce ions. May dissolve in H2O, but does not what? Dissociate into ions. Therefore, there is no movement of ions. I've explained the difference between strong electrolytes, weak electrolytes, acetic acid, for example, here, this should have, and by the way, this equation here, should look like this. CH, that equation should look at CH, OOH, and then aqueous pi, for some reason, doesn't want to go to doesn't want to go to the product side, which is CH COO negative plus H2O. If we have of course here plus H2O liquid on the product side, and then hydronium ion like that, just to balance the equation. Just to balance the equation here, you are shown only the cation, but ammonium, I mean the acetic acid plus liquid H2O in dynamic equilibrium doesn't want to dissociate. This arrow here indicates chemical equilibrium, okay? And it does not completely dissociate. The only hydrogen ion you see, even though we have that, is only about 1% dissociation, around 1% dissociation for weak electrolytes. Here is a good question. All right, learning check. Typical question in an exam, testing you on whether you know the difference between an electrolyte, non-electrolyte is this: which solute will cause the light bulb to glow most brightly? Okay. They all look alike, all right? If you try to use trial and error and say which one will have, or I should see sodium and stuff like that, you need to know which one are molecular compounds here. If I look at the sodium, this is ionic compound. There is a metal and the polyatomic ion hydroxide. This one doesn't have a metal. These are just molecular compounds. And we say molecular compounds, they are non-electrolyte or could be weak electrolyte. But the question is most brightly. So we are looking for ionic compound. And the correct answer is sodium hydroxide, because, all right, because it is ionic compound and 100% dissociation to produce ion in liquid H2O. The correct answer is B. So the point is, unless you know how to classify, if you don't know how to classify compound as ionic compound, molecular compound, or strong acid, weak acid, this will be a challenge to you. So read more on electrolytes. I will have more resources to pack up this. All right, let's move on to 4.3 precipitation reaction. And at the outset, you should know that there are about 7 types of reaction, reaction. One, all right, there is precipitation reaction. That means you mix two things. This is liquid, clear liquid, and a solid fall. These are the reaction which produce a solid product. Let's use a generic chemical equation. All right, A aqueous plus B aqueous to form C in solid plus maybe D aqueous. The solid here indicates precipitate. We consider this as precipitation reaction. Precipitation reaction. We have two combustion reaction. And it involves reaction between an element or a compound with oxygen, you know, combustion involves oxygen. There is what? Acid base neutralization. There is a single replacement reaction. We're gonna come back to this single replacement reaction. Metathesis or double replacement, double replacement reaction, double replacement reaction, double replacement reaction. So now I have that. Double replacement reaction. 6 redox reaction. We call these two types of reaction: oxidation reduction reaction. These are about 6 or so type of reaction. Okay, you'll make your own notes on all this, but first 4.2 is on precipitation reaction, and I've explained to you what a precipitation reaction. If two reagents which are liquid, if I have here reagent A and I have reagent B, and I mixed it too, right? A solid fall down of the solution. We call that precipitation reaction. A solid is formed. A solid is formed. Here is an example. Maybe I can blow up this so that you see the equation. Between reaction between potassium iodide in one beaker and lead 2 nitrate, be able to name your compounds. This is lead 2 nitrate solution in another beaker. The product here, there is a solid being formed here, and this is lead 2 iodide. And of course, potassium nitrate is aqueous, means soluble in H2O. The clear portion here has potassium ions and nitrate ion dissolved in it, whereas the solid, the yellow one here, has lead 2 iodide as a solid. PPT is a precipitate. You may see this PPT. This is stand for precipitate. Precipitate what? Precipitate reaction. When two solutions containing soluble salts are mixed and insoluble, this is insoluble. Insoluble product. We call that precipitation reaction. That's precipitation reaction. Well, you may ask that, how do you know which one is solid, which one is liquid when you mixed it to reaction? The best way, I'm gonna show you the easiest way, and I will allow you to use in the quiz and in the exam, something which is useful in determining or predicting which one is the solid, which one is the liquid or aqueous rather in the solution. I will use a specific example here. Let's say lead 2 nitrate, this is nitrate, plus potassium what will be the product? All right. I know this is a precipitation reaction, but assuming that I don't know, how will I know? Well, according to the text, you need to memorize and learn the solubility rules, the solubility guidelines. And rule number one, all ionic compounds are soluble in H2O, so you should be able to classify a compound as an ionic. If it is an ionic, then I know it's going to be soluble. For example, here, lead 2 nitrate, this is an ionic compound, there is lead, there is polyatomic ion nitrate, and it's aqueous. And by the way, if I know this is also aqueous, all right, potassium is metal, chloride is non-metal. It is an ionic compound, all right, but not all of them are what? Are soluble. Not all ionic compounds, most of them, they are soluble. But when I see it's aqueous like that, I know they are soluble. But nevertheless, you are expected to memorize the solubility guidelines. That, all right, all nitrates are soluble. So if anything, with the nitrate at titrate, then you know what? It is soluble. All acetate, all right, all compound with acetate ion, they are soluble. All chloride except silver chloride, mercury 2 chloride, and lead 2 chloride. These are the rules you are expected to memorize. Compound containing sulfide, look at the exception. Compound containing carbonate, look at the exception. All right. So before we look at the example here, all right, how will you know which one is the product in this example on my whiteboard? It's assumed that this is what you will do, okay? That when you mix the two reagents where you have lead, and you have to write the cations plus nitrate, polyatomic ion. Forget about the, this is going to be in the next equation, PPNO3 2 aqueous plus JCl aqueous. We want to know the product on that side. Assume that you have what? You have the cations and an ion in the reaction flask. Our second reagent will give us potassium and chloride, potassium and chloride ion. They will exchange the anion. Cations will exchange the anion. This is by the here is negative 1. I'm going to say negative 1. This will combine with this, and that will combine with that. If they are exchanging double replacement, we're going to come back to that. They are exchanging, the cations exchange the anion. Negative, they swap or exchange the anion, the polyatomic ion or monoatomic ion, so that you write the correct formula for the product, which means I will have, look at this, I will have PPCl2. Some students just think that if that one is combining, why don't I just have Cl? No, you are breaking the what? the rules. Use the crossover rule there to write the correct formula. Therefore, the subscript come down there plus KNO3. KNO3. Potassium +1, nitrate -1. So it's going to cancel out that. Always do that. And remember to balance the equation. If I look at silver, lead, we have one lead, we have one lead. So lead is taken care of. But here, balanced polyatomic ion as if it is a single unit. So nitrate, we have 2 nitrates, we have 1 nitrate on the product side. So what I'll do is put that 2 in front of nitrate, potassium nitrate, and we need a 2 in front of potassium chloride. We need 1 in front of lead, 2 nitrate. So the equation is balanced. Always get into the habit of balancing the equation. But the question is, how do we know which one is the precipitate, which one is just aqueous? From what we looked at earlier on, all right, from what we looked at earlier on here, all nitrates are soluble. So this will be aqueous. So if you have nitrate, this will be aqueous. And I don't want you to say that, once I know this is aqueous, the other one is solid. There is a table which I'll give you in the exam, right? Here is the table I want us to learn how to use. This is not what I wanted to share. Yeah, this is what I wanted to show you. And I will allow you to use this in the what? In the exam. I'll allow you to use this in the exam. All right. Well, you have to look at, if you look at this table, we have cations on the first column. Cations, these are the cations, positively charged, positively charged. Be careful, this is not the exclusive, but it works 90% of the cations you'll be dealing with. Of course, some of them may not be on the chart you see here. You need to supplement this with the rules. Of course, if you learn the rules, it complement this, but this is one quick, easy way of identifying which one is soluble. Understand what these notation, the symbols in the boxes. AQ, remember AQ means aqueous, dissolved in what? Dissolved in water. S means solid. So when you see something here, solid means liquid, or that means it decomposes. So if I'm looking at the lead 2 ion, which is second here, and the chloride, look at where they intersect. The intersection is right here. This means solid. That means it is insoluble. So I'll write a subscript for that solid. I can have something else. Let's say, for example, barium with carbonate right here. I know it is insoluble. Calcium with chloride, ion here, calcium with chloride. Calcium is here and chloride is here. They intersect, it's aqueous. It is aqueous. Decomposing means it doesn't even, last. Like as soon as form, maybe just decompose and break, and we don't have the decomposition. For most part, you will be focusing on the precipitate. Having shown you how this table works, I want you to download, print, because you'll be using for your homework assignment and in the quiz and also in the exam. So get used to reading this table. Unless you memorize the rules, that's fine, right? Let's go back to our slide here. And on the whiteboard, I will have this as solid. Using that solubility chart, I will predict, or I've predicted that the product PPCl2 is solid, even though here, unless you memorize the rule, lead 2 chloride, It's insoluble, therefore it's solid. Therefore it's insoluble. So take home message from here is instead of memorizing these rules, you will use the table I gave you in the exam. Make sure you know how to use it. Make sure you know how to use it, all right? So here is a question on solubility. What species, all right, are present in solution of? That means when it dissolves. This is a cation, anion, and I may just go back to this. I don't know if we have potassium. If we don't have potassium, we can use anything on group 1. We can use anything because they belong to the same family. Group 1, metal with cyanide. We know they are all soluble. I don't have cyanide here, but group 1 are soluble. KC, there is the cyanide. All right, KCN, this will break down here to give us potassium and cyanide, SNA negative. That is cyanide, KCN negative like that. All right, no, it's gonna be what, not negative, but I wanted to say this is CN negative, cyanide ion, and the correct answer is D. It will dissociate to give you that, okay? I've given you how to predict the ionic ionic compound, the solid in a solution. All right, know the ion present. Okay, if you don't know how the ion present, you won't be able to write the correct formula for your compound. Consider possible combination when to exchange that. Look at page 127. All right, magnesium hydroxide. Let's see if it's true that magnesium hydroxide is insoluble. If I look at the all nitrates is always, all nitrates are always what, soluble. So if I have magnesium hydroxide, magnesium and then hydroxide is right here and it is insoluble. Remember magnesium group 2 and hydroxide negative. This will give you Mg. This is the correct formula, magnesium hydroxide, magnesium hydroxide. This is what I was doing in showing you that this is solid, how to predict the precipitate a solid in a reaction. Learn how to use that table I just gave you. It will help you in the homework assignment and in quizzes as well. Metathesis reaction is a double replacement. Metathesis exchange, okay? Metathesis reaction look like this. If I have A, look at this, A, B plus C, D. In metathesis reaction, this is considered as cation, this is anion, this is cation, this is anion, can be polyatomic ion. A will combine with D and D will combine, C will combine with B. And remember, we start with the cation, writing the correct formula for ionic compound. So here is A, D plus CP, not PC, CP, because this is a cation, this is an ion. This is a cation, that is a noun. Make sure you write it. They exchange, double replacement reaction. Double replacement reaction means to transpose. All right. So for exchange reaction, double replacement ions, they exchange that. If you look at hydroxide, it has combined with magnesium. Nitrate has combined with the sodium. They exchange the anions. Well, there are three types of equations For every metathesis, there are 3 steps, which we are going to look at in a moment: completing and balancing metathesis equation. Balancing. What I have here is not balanced. We don't know what it is, but we're gonna look at that. So step number 1 is to write the correct chemical formulas for the reactants and the product. Remember what we said earlier on for lead to nitrate plus potassium chloride. So if you don't know how to write the correct chemical formulas, it's gonna be hard to balance the equation. Write the formulas for product cation from one reactant and the other. Use charges to write proper subscript. This is where the double replacement comes in. Remember how I did this? This is what I did here in terms of using the charges to write the proper subscript. What that means is lead, for example, this lead right here, and chloride, lead and chloride will form PbCl2 using the crossover rule. Otherwise, you'll write, or you risk just writing this. I see sometimes PCl, this is wrong. Make sure you use the correct equation. Check your solubility rules. Of course, using the solubility chart, predict which one is solid, all right? And then lastly, balance the equation. Make sure that the kind of atoms on either side do add up. Should be the same, okay? There are 3 types of equation. We need to learn how to write them. We have what we call molecular equation, which up to this point, we have just been balancing the molecular equation. We will look at the special type of equation we call complete, and then how to write the net ionic equation. The way this have been presented, you will be working your way home to write the net ionic equation starting from the molecular. If you miss the molecular equation, it doesn't really matter how hard or careful you are with step 2 or equation 2, equation 3, you'll get it all wrong. So it's important to get equation 1, molecular equation 1, writing the correct chemical formulas. 2, balancing it. So 2 things in step number 1, you have to make sure you balance. For example, this is lead to nitrate plus potassium chloride, okay? If we write the correct formulas for that, this will be PbC, this is nitrate plus HCl this is solid, by the way, this is solid right here. Here is what we call molecular this is molecular equation. We are in step number 1, molecular equation. We need to balance the equation. We have 2, or we need a 2 in front of potassium chloride, and we need a 2 there. There is a 1 here, there is a 1 here. The equation is balanced. Make sure that equation 1, molecular equation, is balanced. Then we have what we call the what? Complete or sometimes we call this total ionic how do you generate complete ionic equation or total ionic equation? there's a note which I want you to pay attention. Split all AQ in molecular equation, If you have solid leaf, if you have liquid leaf, if you have gas leaf. So we do not split. What do I mean by splitting? I'll go back and see where we have the cation. I'm gonna split the cations from the anion. You have to see where you're splitting, not the nitrogen and oxygen, no. Cation and anion. I'll split this. No, we don't split solid. So this is just the way it is, PPCl2. What I wanted to split is this aqueous, and by the way, this is AQ. And I'm gonna split this one as well, because it is what? It is aqueous. So the ions you will take from here is, this is going to be the ions. The subscript here changes to the coefficient. That means 2 nitrate, and it has an overall charge of negative. Don't forget the charges. Take note of the subscript for nitrate here has changed to the coefficient of nitrate in complete ionic equation. Those are the ions from the first reagent, plus 2 positive plus 2 negative. And please include the physical state. This was aqueous. We leave alone solid, so this is going to be just PPCl2 solid plus 2K positive aqueous plus 2NO3 negative. And this is aqueous. So I've split the what? I've split the aqueous into cations. We have what? We have cation, lead. We have the anion, polyatomic ion nitrate. We call this complete ionic equation, So if we had not balanced the equation, molecular equation, chances are we will not even move beyond the molecular equation. Make sure you balance your equation. And then lastly is the net what? Net ionic. How do you generate the net ionic equation? Note here is you cancel spectator ions in complete ionic what? So we need to cancel, we need to remove the spectator ions, and whatever will be left on the equation will be the net ionic equation, What do we mean by spectator ions? Those ions which look alike on either side of the reaction arrow, all right, are spectator ions. Back here, these are spectator ions. If I look at the nitrate, it looks exactly the same as the nitrate here. So we need to cancel that on either side of the reaction arrow. If I look at what the potassium, and potassium, they look exactly the same, but chloride is not the same as the chloride in lead to chloride. No, just change. So if I write the net ionic equation for this, it's going to be PP2 positive aqueous Cl negative. Aqueous, please indicate the physical state, giving us PPCl2. And that is the net ionic equation, So the one common mistake students make is failing to balance the equation. Two, failing to identify which one is the precipitate, which one is the solid. Otherwise, if you don't know which one is the solid, you know which one to split. If you have a solid, if you have a liquid, or if you have gas, do not split in generating the complete ionic equation, and that will affect the complete ionic equation unless you do it, unless you know what you're doing. Okay, so that's just an overview of writing the metathesis reaction. I've given you molecular equation, list the products without indicating the ionic nature of them. They only list overall reaction and the state. Here is an example. You see this? This is what I just used this, and it's not just by accident that we have solid in here. From what? From the solubility rules. In complete ionic equation, all strong electrolytes, strong acid, strong bases, soluble ionic salts are dissociated into ion. That is what I meant by splitting, dissociate the ionic compound. All right. So the solid will remain just solid. We don't split that. The rest can just be split into cation and anion. And please take note of the subscript here. It will change to coefficient. The subscript here will change. These are two nitrates, but it just changed to coefficient in the complete ionic equation. Complete, you don't do anything, that's complete ionic equation. And then lastly, net ionic equation, we count the spectator ions. To form the net ionic equation, cross out anything that does not change from, it look the same on either side, we call spectator ions. The ions cross out are called spectator ion. Nitrate, you see how I cancel this? Nitrate and potassium cancel out because they are spectate, they don't participate in the formation of the solid. The remaining ions are the that form the product. What we mean by the product is the solid product. The solid product, insoluble, the precipitate. We need to keep track of the precipitate for that. And that is our what? And by the way, I think this is, yeah, they are using iodide. I use chloride, iodide, chloride, they are in the same group. They react the same way. Instead of lead to iodide, I have lead to chloride. So that's the question for, that is the last equation you will be asked. Please look at the end of chapter problems. Practice with worked examples. If you have any question, please send it to me, schedule Zoom meeting, or use the SI support session to, if you need further assistance on writing the net ionic equation, complete ionic equation, and the molecular equation. All right, so that's what I wanted to go over in that. Let's see which ions, if any, are spectator ions in this chemical reaction. So I'll see that chloride formed the solid, so I'm just gonna cancel anywhere I see chloride. Anyway, I see silver, so A is wrong because we have silver. Well, yeah, B nitrate is okay, but the chloride is wrong. So A and B are wrong. And lastly here, sodium and nitrate ion, they are the spectator ions. Just gonna cancel out that. D, of course, is wrong. So the correct answer for that is C. C, which is Na sodium plus nitrate, like that. This is a typical question in the quiz, that which one of the following is or are spectator ions, or what is the net ionic equation for the following chemical reaction, or what is the complete ionic equation for this? You have to use the, all right, you have to use the solubility rules. You should be able to balance the equation in order to answer that question. Well, let's move on to 4.3, acid, bases, and neutralization reaction. First of all, we will look at the definition of an acid, definition of a base, before we look at the neutralization reaction. There are three types or three versions of the definition of a base, all right? Acid and a base here. And three types. I don't know if I'll have enough space. All right. You should draw a parallel. There is Arrhenius, and then two guys, prostate, Lowry, prostate, Lowry. Maybe you cannot see that. I'm just gonna erase this and then have it somewhere here so that you see clearly their names. So Arrhenius, and then prostate, Lowry, and then the Lewis definition. An acid is simply any substance that produce H plus in water. Anything that produce, or any substance that produce hydrogen ion in water is Arrhenius. And then anything that produce OH in H2O is Arrhenius. No, not here. I mean to say here is simply they define as proton donor. Proton donor. Arrhenius acid, any substance that produce hydrogen ion in water, when dissolved in water, is Arrhenius acid. Proton donor is prostate Lowry. And then here is electron pair acceptor. It accepts electrons. The definition of a base is any substance that produce hydroxide ion when dissolved in what? E.g. NOH, anything that produce hydroxide ion when dissolved in water is Arrhenius space. Arrhenius space. Bronsted, all right. Laurie Bronsted definition, just we define this as proton acceptor. It accept. You got to be careful because in the quiz, in the exam, I may ask you the definition of an acid according to Bronsted or according to what? Arrhenius. Here, Lewis acid or Lewis space rather is electron, and you got to specify electron pair what? Pair donor. That means it donates electron pair. For example, here, NH, if you recall, electron dot symbol for Na3. There are two lone pairs of electron. We consider this as a base electron pair donor. I'll recommend you learn, distinguish between the two, the three definitions of an acid, so that when we say acid bases, there are three versions of the definition of those terms. But in general, any substance that produces or ionizes in H2O to form hydrogen ion. This is hydrogen ion, okay? Call this hydrogen. It doesn't want to stay by itself in H2O. If this is taking place in H2O, remember this is the molecular geometry of H2O. It gets associated with this produced oxygen, with this produced hydrogen ion, and you'll see this as hydronium ion. Anything that produces hydronium ion is an acid. So hydrogen ion and hydronium ion can be used interchangeably. Sometimes we call a proton. This is an example, HCl. All right, HCl is an acid, nitric acid, sulfuric acid, acetic acid, to give you just few examples of acid. Bases are substances that react with or accept hydrogen, proton acceptor. Okay, they produce that. Here is an example of ammonia, Bronsted base, proton acceptor. It's accepting proton to form ammonia, to form ammonium ion. We have strong acid, we have what we call weak acid. And this is what I always recommend, that in Chem 2, you will be expected to remember what constitutes strong acid, what constitutes weak acid. Now, strong acid completely dissociate, all right? Weak acid partially dissociate. What do we mean by dissociation? This is a strong acid, HCl, which will dissociate to give us 100% hydrogen ion aqueous, but this is a strong acetic acid. This is an example of acetic acid. You'll see over and over again. It doesn't want to go to the product side. See double arrows. It is pointing predominantly towards the reagent. So here we have this aqueous, and this is aqueous. It will just say as the molecule acetate ion CH3COOH negative plus hydronium ion. Let's say we are adding H2O for that. liquid H2O will combine with hydrogen ion to form hydronium. This is hydronium, this is the acetate. It's generally about 1% dissociation. So if we have 100 molecules, 1% will dissociate for a weak acid, A strong acid completely dissociate. Likewise, for strong bases, they dissociate completely, and hydroxide ion will give you that. These are just few common table 4.2 common strong acids and strong bases. You need to remember what constitutes strong acid, what constitutes strong bases. It's just few examples. Group 1 hydroxide, lithium chloride, lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. Few common strong acids. Now, asking yourself, I think we talked about the strong electrolytes with electrolytes earlier on. I don't want to go back to that, but remember in this section, strong acids are always strong electrolyte. Weak acids are always weak electrolytes, all right? But how do you know that this is a weak acid, this is a strong acid? How do you know that this is a strong acid, weak acid? All right, you need to memorize those, what constitute weak acid. Here are a few examples of weak acid. CA3, COOH, acetic what? HF, this is hydrofluoric acid, all right. HNO2, these are nitrous or acid. Just to give you a few examples of weak electrolytes, all right. These are weak which they do not dissociate completely. Okay, we have looked at the strong cases, all group 1 hydroxide, including ammonia, they are weak electrolytes as well. Okay, please go back, make your own notes on that. Let's see, neutralization reaction is a reaction where an acid and a base react. And in this case, an acid and a base such as NaOH, this is a base because it produces hydroxide. There is a hydroxide ion plus HCl. This will form sodium chloride aqueous plus H2O. H2O, this is an example of neutralization reaction. Because an hydroxide ion react with hydrogen ion to form liquid H2O. When we write, of course, the net ionic equation, or even in this section, you'll write the net ionic equation. Common two products in acid-base neutralization. Acid-base neutralization are water, plus salt. This one is ionic what? Ionic compound, ionic compound. Those are the two things you need to remember: water and salt, an ionic compound, and H2O. This equation can be also written as molecular equation, complete ionic equation, and the net ionic equation. HCl, this is an acid strong base. This is molecular equation. We can split this. Remember, we don't split liquid. When writing the ionic complete ionic equation, we will split that wherever we do that. So this is molecular equation. What you see here is the complete ionic equation. We do not split the liquid. Look at the liquid. Maybe I can just even zoom this so that you look at. This is the molecular equation. This is the complete equation to complete ionic equation or total ionic equation. And what I was saying is you do not split the liquid. You do not split the liquid. And then finally, we have the net ionic equation. A net ionic equation for acid-base neutralization always produce what? Always produce the liquid H2O at the end. But be careful wherever you are writing the net ionic equation for the weak acid, okay? Whenever you are writing the net ionic equation for the weak acid, and maybe I can use an example on that for weak acid so that you don't end up, all right, for weak acids so that we know how to for weak acids such as CH3COOH plus sodium hydroxide, for example, right? Sodium or not sodium acetate, but I can write this as CH. The hydrogen will combine with hydroxide to form liquid H2O. The hydrogen here will combine, and by this is aqueous, this is aqueous, this is aqueous, this is ON. This is equation 1 molecular. For complete ionic equation, since this one does not dissociate completely, in H2O, we will have CH3COOH. It's just stayed the way it is, plus CH3COO aqueous plus CH3COOH plus Na positive plus liquid H2O. So that when we cancel, this will go with this will go with that. We remain with hydroxide. We remain with hydroxide, and the way it is liquid. plus liquid H2O. There is liquid H2O on the other side. Because there is no the molecular acetic acid will not dissociate completely for the weak acid. There is an example in the text as well for barium hydroxide. Look at the reaction between acetic acid and barium hydroxide in the text to see how the net ionic equation is written for weak acid. Moving forward, the last thing I want to look at is the neutralization reaction, which involve the formation of gas. In this case, there is the carbonates, all right, acid with carbonates plus hydrogen carbonate. This is CO, that is anything with that, and then there is hydrogen carbonate. And in the same way, you will write the net ionic equation, neutralization reaction. This reaction which cause or contain carbonates and bicarbonate. Bicarbonate is hydrogen carbonate, and of course that always they produce H2O and CO2. This is gas, and it's just gonna escape. The two products here are always there in gas forming reaction. So when we talk about the gas, this is the gas being referred to, even though there is hydrogen sulfide later on. I want you to see what happened in this reaction. So if you have calcium from the first reagent, calcium and carbonate ion, hydrogen ion, and chloride ion, if this is the reaction vessel, we expect this to form calcium chloride, which is what we have here. So calcium. Now, look at this. If this combined with that, you expect to have this carbonic acid, right? But it's unstable. This is unstable. H2CO3, unstable. And as soon as it is formed, it will decompose into H2O plus CO2. So wherever you have this type of reaction where hydrogen carbonic acid H2, you expect to have this, know that you have to break it down to hydrogen, liquid H2O here and CO2. And of course, when you write the net ionic equation, we will not split the liquid, we will not split the gas, we will not split the liquid, we will not split the gas. This is hydrogen, sodium hydrogen carbonate. This is bicarbonate, strong acid hydrobromic acid. Sodium will combine with, and this will form liquid. You will have expected hydrogen to combine with that. It's going to break down to CO2. It's going to break down to CO2. You have to know the two products you expect from carbonates and bicarbonate, liquid H2O and CO2. Last type of gas you see are those with the sulfides, right? Sulfide, like that, sulfide produce what? Hydrogen sulfide. This is the gas produced, and this is hydrogen sulfide gas. So I'm just gonna look at the hydrogen sulfide, see how those will be formed. Sodium sulfide plus sulfuric acid neutralization reaction. This is an acid plus the sulfide. Na2S, this is sodium sulfide. IDE with sulfuric acid will produce sodium sulfate and hydrogen sulfide gas. This is the idea of the rotten eggs, okay? So I'll be careful with hydrogen gas. Those neutralization reactions which produce gas are carbonates with an acid, hydrogen carbonate with an acid. Those two produce liquid H2O and CO2 gas. And the gas being referred for sulfides, all right, is hydrogen sulfide gas. This is gas right here. And I have that. And shouldn't be that difficult for you. Now, putting chemistry to work, we all know anti-acid neutralizes the acid producer, of course, and all of them, they are either carbonate or hydrogen carbonate. That marks the end of part 1 or part A of chapter 4. We'll come back again to chapter 4, part P, chapter 4, part P. Until then, have a great day, wonderful time. We'll meet again in part B. Thank you.